inside this processing plant. A single decision made in the next 90 seconds determines whether 5 tons of spiky durian shells become premium biomass fuel worth thousands, or industrial waste that shuts down the entire recycling line for hours. The decision window is razor thin. Moisture content, particle size, feed rate. If any of these parameters is off by just 8%, the industrial grinders jam within minutes, the dryers overheat, and production stops cold. This happens every single batch, multiple times per day. And what makes durian shells different from any other agricultural waste is about to become clear. This facility processes over 12,000 kilograms of discarded durian shells every day. What fruit markets throw away, this plant transforms into 3 high-value products. Biomass fuel pellets that burn cleaner than coal. Organic fertilizer base. Activated carbon material. But durian shells are dense, fibrous, and structurally unpredictable in ways that standard biomass isn't. One shell can have moisture content at 15%, the next one at 35%. This variability separates successful facilities from failed ones. We're here to understand the critical decisions that prevent this line from grinding to a halt. The recycling line has 3 main zones. Zone 1. Shell collection and initial sorting. Shells arrive from fruit processing facilities. Workers remove contaminants and separate shells by visual moisture level. This initial sorting sets up everything that follows. Zone 2. Size reduction and moisture control. Shells are fed into industrial grinders that break them into fragments, then move to rotary dryers where moisture is reduced to a controlled range. Zone 3. Final processing and product formation. Dried fragments are either pelletized for fuel, composted for fertilizer, or processed into activated carbon. But here's what most people don't realize about durian shells. Their fiber structure is closer to wood than to fruit waste. Internal layers contain natural resins that make them highly flammable when dry and nearly impossible to grind when wet. This makes the next decisions absolutely critical. Critical decision number 1. Before any shell enters the grinder, operators must assess its moisture content. Fresh durian shells can hold anywhere from 20 to 40% moisture. From an engineering perspective, moisture is the single most important variable at this stage. If shells with high moisture go directly into the grinder, the fibrous material clumps together instead of breaking cleanly. The grinder blades slow down. Heat builds up. Within 3 minutes, the machine overheats and shuts down automatically. If shells are too dry, they shatter into inconsistent sizes, creating dust that clogs the conveyor system and poses a fire hazard. Here's the decision. Shells must be pre-sorted by moisture level before entering the grinder. High moisture shells are set aside for pre-drying. Medium moisture shells go directly to grinding. An experienced operator can tell moisture level by the shell's weight, surface texture, and how it sounds when tapped. In advanced plants, moisture sensors scan incoming batches and automated gates route shells to the correct path. But an operator who misjudges a batch can feed wet shells into a grinder running at full speed. The result is immediate. The grinder jams. The line stops. Clearing a jammed grinder takes at least 2 hours and often requires complete disassembly. Think of it like grinding wet durian shells is like shredding soaked cardboard. The fibers don't separate, they compress and bind. But here's what makes this decision even more critical. Unlike other biomass materials, durian shells don't show moisture damage on the surface. A shell can look perfectly dry outside, while inner layers still hold 20% moisture. This is why visual inspection alone isn't enough. No second chances. Critical decision number 2. Once shells are cleared for grinding, the next decision is feed rate. Industrial grinders operate with rotating hammer mills or knife blades, handling several hundred kilograms per hour, but only if material is fed at a controlled, consistent rate. The decision is deceptively simple. How fast do you feed the shells? Too fast, and the machine becomes overloaded. The blades can't keep up and the motor stalls. Too slow, and production capacity drops by 30% or more. From an engineering perspective, ideal feed rate depends on shell density, moisture level, and blade sharpness. In modern facilities, automated conveyors manage this. Sensors measure the grinder's power draw in real time. If the motor pulls too much current, the conveyor slows automatically. But here's where process stability is tested. If moisture sorting in Zone 1 was even slightly inaccurate, feed rate control must compensate. A batch that looks dry but retains moisture inside behaves unpredictably. The power draw spikes. The operator must decide, slow the feed and lose throughput, or push through and risk a jam. This is why every decision connects like links in a chain. Industrial operators don't just control one variable. They manage a system where every parameter influences the next in real time. At industrial scale, there's no time to adjust once the grinder is overloaded. The margin for error is measured in seconds, not minutes. Critical decision number 3. After grinding, shell fragments move to rotary dryers. These are large cylindrical drums, heated internally, rotating continuously to tumble material and expose it to hot air. The target is reducing moisture from 15 to 20% down to 8 to 12%. This range isn't arbitrary. It's the difference between a product that burns efficiently and one that smolders or ignites uncontrollably. The decision involves 2 parameters: dryer temperature and retention time. If temperature is too high, outer layers dry quickly, but inner fibers remain damp. This creates case hardening. The material appears dry but fails quality tests. Worse, overheated fragments can spontaneously ignite. Durian shells contain natural oils and resins flammable at temperatures above 140 degrees Celsius. A dryer fire doesn't just stop production. It can destroy equipment worth hundreds of thousands. If temperature is too low, drying takes too long. Material backs up and throughput drops. Retention time is equally critical. If fragments move through too quickly, they exit under-dried and must be reprocessed. If they stay too long, they overdry, become brittle, and produce excessive dust. Here's where precision becomes everything. Dryer temperature is set based on incoming material moisture. Retention time is controlled by adjusting drum rotation speed and internal flight angles. In advanced facilities, infrared sensors at the dryer exit measure actual moisture content in real time. If readings fall outside target range, the system automatically adjusts within 30 seconds. But this control depends entirely on the grinding stage. If shell fragments are inconsistent in size, some pieces dry faster than others. Small particles overdry and turn to ash. Large chunks remain damp inside. And here's the difficult part. Operators can't see this happening until the batch exits. By then, it's too late to correct. A dryer running just 10 degrees too hot for 2 hours can carbonize an entire batch. That's over 800 kilograms downgraded to low-value compost. At current market rates, that's over $1,500 lost per batch. In a facility running nonstop, that loss compounds every shift. Critical decision number 4. Once fragments are dried correctly, they move to the final decision point: product stream separation. Not all dried durian shell material is the same quality. Clean, uniform, dense fragments go to pelletization for biomass fuel, the highest value product. Lighter, more fibrous material with residual contaminants routes to composting for fertilizer base. A small percentage of highest quality fragments are reserved for activated carbon processing. The decision here is about sorting and routing. If high-quality material is sent to composting, the facility loses revenue. Biomass pellets sell for 3 to 4 times more than compost base. If contaminated material goes to pelletization, pellets fail quality standards and get rejected by buyers. In smaller facilities, this sorting is done manually. Workers visually inspect dried fragments and separate by hand. In larger plants, automated optical sorters use cameras and air jets to separate material based on size, color, and density. But this decision depends on everything that came before. If moisture control was accurate, fragments are consistent and easy to sort. If drying was uneven, sorting becomes difficult and error rates increase by 20%. In high-volume plants, separation happens at speeds exceeding 2 tons per hour. Each routing decision must be accurate. If contaminated material slips through to pelletization, entire batches worth thousands can be rejected at quality inspection. There's no room for guesswork here. Across every zone, control systems monitor critical parameters. Moisture sensors at shell intake, powered draw monitors on grinder motors, temperature probes and infrared scanners inside dryers, optical sorters and density sensors at final separation. These systems don't just measure, they prevent. If a parameter drifts outside target range, alarms trigger and operators intervene before problems escalate. In automated facilities, the system adjusts itself within seconds. This level of control makes industrial-scale recycling viable. Without it, processing 12,000 kilograms of unpredictable agricultural waste daily would be impossible. In industrial practice, prevention is always cheaper than downtime. A jammed grinder costs 2 hours of lost production and $500 in labor. A dryer fire can cost days of repairs and tens of thousands in equipment damage. That's why every critical decision point is protected by monitoring, automation, and operator oversight. By the time finished products leave this plant, they've passed multiple quality checkpoints. Moisture content, particle size, density, contamination level. Each parameter is a direct result of critical decisions made earlier. If initial moisture sorting was accurate, grinders ran smoothly without jamming. If feed rate was controlled, grinding was efficient and produced uniform particle sizes. If dryer temperature and retention time were optimized, fragments dried evenly without carbonization or fire risk. If final sorting was precise, each product stream meets quality specifications and commands premium pricing. These decisions also impact sustainability at scale. Proper processing converts agricultural waste that would otherwise rot in landfills into valuable products, reducing environmental burden and creating renewable energy sources. In a facility processing tons of material daily, even a 5% improvement in yield translates to significant environmental and economic impact. This recycling line operates continuously because every critical decision is controlled, monitored, and executed with precision. Moisture assessment, feed rate control, dryer temperature, product separation. Each decision happens in moments, but their impact determines whether the line runs smoothly or stops cold. This is what makes industrial recycling possible. Not just processing waste, but transforming it into measurable value. Not just operating machines, but managing complex systems where every variable matters and every decision connects. From an engineering perspective, Durian shell recycling is a perfect example of how process control turns unpredictable agricultural waste into consistent, high-quality products. The difference between smooth operation and a costly shutdown is often just one wrong decision at one critical moment. And in a facility running nonstop, that difference is everything.